Here is an example. I asked it in the quiz. So which of the following setup has the maximum magnetic field at the center? Assume conductors are placed at the four corners of a square and dot cross indicates the current direction. So we know that dot is current coming out of the, so current is a vector quantity. So if you see a dot, that's a vector coming out of the board. So vector is nothing but you know that we indicate with an arrow. So when arrow is coming towards you, we will see the dot, and when arrow is going into the board, you see a cross. That's what it is. So the dot indicates current is coming out of the screen, cross indicates current is going into the screen. Now our question is find the magnetic field at the center. So if we look at the first setup, so let me take, this is conductor 1, 2, 3 and 4. There are 4 conductors. So because of the conductor 1, current is going into the board. So the magnetic field, if you use the right hand rule, the magnetic field is rotating in clockwise direction. Okay, so the thumb indicates the current direction, the folding fingers indicates the magnetic field direction. So if you look at, if you fold your fingers, it's going in clockwise direction. Now if you look at the dot, current is coming towards you, that magnetic field is in anti-clockwise direction. Okay, so now if you look at these 4 conductors, conductor 3 is clockwise, conductor 4 is anti-clockwise. Okay, now we want to find magnetic field at the center, at center B. Now because of the first conductor, remember, so magnetic field is always circling or rotating in around the conductor, but magnetic field at any point is tangent to that circle, right? So if this is in this direction, so that's tangent to circle, that's tangent to circle. I may not be 100% drawing it properly, but that's what it is. Now, so because of the conductor 1, can I say, so the magnetic field, so if I draw a circle, can I take that as B1, conductor 1? How about conductor 2? Conductor 2 tangent to the circle, that's B2. Conductor 3, that's B3. Conductor 4, that's B4. Okay, so at the center, I didn't draw according to the scale, assuming every current is same in this case. So B1 must be equal to B2, must be equal to B3, must be equal to B4. So they cancel out each other. So for this, B at the center must be equal to 0. Now coming to the second case. So the second case, here is my magnetic field direction. So I'm still taking 1, 2, 3 and 4. So because of the conductor 1, it's going to be, that's my B1, and conductor 2, this is also a cross. So can I say my B2 is in this direction? Okay, now B3. Okay, so here is my B3, or sorry, that's a 4th conductor. So my B4 is going to be the same direction. So this is my B4, and B3 is going to be something like this. That's my B3. Okay, so for set 2, I have 2 magnetic fields, both are in the same direction, and 2 magnetic field going down. Okay, so what happens? The y components cancel out each other. At least I'll have a x component. Okay, so that's for the second case. Second case, I have some magnetic field. It's on the negative x-axis. Now when it comes to third case, so here is the magnetic field. It is going, so at the center, it's going in this direction. Sorry. Okay, at the center. Okay, here it is. that is coming towards like this. So I'm taking 1, 2 and 3 and 4. So my third conductor is like this, so it's going to be something like this. I'm sorry, this is B4 basically. Okay, if you look at it, it's going to be something like this. This is my B3. This is third conductor, that's the fourth conductor. Okay, it's going to be in that direction. So this is B1, B2. So here also B1 equal to B2 equal to B3 equal to B4, but they're all opposite to each other. So the total magnetic field is going to be 0. So in this case, for the second set, I will have the maximum amount of magnetic field. Thank you. Now I want to explain one more example. I didn't ask you this in the quiz, but this is another important question I want to go through. So a negatively charged particle in a uniform magnetic field B moves in a circular path. Remember, if you place a charge on a magnetic field, it basically goes in a circular path, but the magnetic field is like this, a straight lines. Okay, so it will be going around like this. Okay, it will exit. So it's called cyclotron motion. Now the question is, a negatively charged particle in uniform magnetic field B moves in a circular path. So assume that this is moving in a circular path. So magnetic field is coming, or sorry, so the cross indicates that the magnetic field is going into the screen, and here is the velocity. Okay, or with, I mean, it's rotating in a clockwise direction with the radius r. So which of the following graph best describes how the frequency of revolution f of the particle depends on the radius r? Okay, now I think I shared with you a video. By the way, let me talk about this. So the force on this must be F equal to Q V B, where B is the magnetic field, Q is the charge, V is the velocity. Okay, this is velocity, how fast it is moving, B is the magnetic field, Q is the charge. Okay, so since it is moving in a circular path, I can say this is mass times acceleration, and I can say mv square over r, where v is the velocity, r is the radius. Okay, now if I combine these two equations, r, so the radius r equal to, I will end up with mv over q times b. That's the radius. So if I have more velocity, more radius. Okay, so radius and velocity, they are related. Now but here he's asking about the frequency. So now frequency is nothing but 1 over time. That's a time period. Can I write this as v over 2 pi r? So basically velocity equal to distance over time. Okay, so time is nothing but distance over velocity. Okay, so frequency is nothing but 1 over time, so velocity over distance. So the distance it is traveling is 2 pi r. Okay, that's circumference of circle. Okay, so I'm going to replace this v. I'm going to replace v with f. So if I replace v with f, I will end up with number of cycles, or f equal to qb over 2 pi m. That's the frequency. Now can I say my frequency is depends upon magnetic field B and the charge and mass of the charge. It is independent of radius. At the same time, it is independent of velocity. So basically, if you look at these graphs, which graph is the proper graph for this? So as since it is independent, it doesn't matter. This is the right answer. So as radius changes, frequency does not change. Okay, thank you.